Right, so our next speaker is Aram Ebtekar for his second talk in the symposium on the theorem of induction of finite data.
Sorry for my voice today. Thank you, Maria. So this is meant to be a okay. So this is more of a philosophical talk, but we'll try to be very precise here about what we mean. The point here is to, in a pragmatic sense, answer the problem of induction, and in the process of doing so, really understand why machine learning theory needs algorithmic information theory. So we'll essentially revise the negative results, which are no-free lunch theorems, which tell us which are a fundamental limitation or obstacle for developing a theoretical understanding of why generalization is possible. And then on the positive side, we'll kind of revisit the result that Solomonoff induction is universal and see how that can be viewed as an answer to no-free lunch. So in machine learning, and indeed in induction, what we want to do is extrapolate from the data we've seen to be able to predict data we haven't seen. This is the fundamental problem of induction, because there's no logical relationship that forces, logic alone does not force any relationship between what you've seen and what you haven't seen. Technically, it's entirely consistent that the unseen stuff is completely unrelated. So the goal of learning theory is to identify when and how it's possible to do this prediction. And it's tricky because we're like, well, obviously, if they have nothing in common, we can't predict. But if they have something in common, we should be able to predict. If there's some pattern. The thing is, we don't know how to formalize what counts a pattern and what doesn't. And this is the concept of no-free. So we can illustrate this with an example. When we're trying to learn a target function, it seems to us intuitively that there's a pattern here. Okay, if f of 4 is 4, and f of 8 is 8, and f of 11 is 11, what is f of 0? Okay, we kind of pattern match. This looks like just the identity. I could have chosen a different pattern, and you would probably still guess it. But in some sense, if you're looking combinatorially at the space of all possible functions, there's no reason for f of 0 to take on any particular value over any other. So the counting argument is, okay, you can actually make the domain range finite too if you prefer, instead of the set of all integers. That way the combinatorics makes more sense. But and then there's an equal number. You can count how many functions there are, such that f of 0 is 0 and also fits to your training data. How many of them have f of 0 equals 1? How many of them have f of 0 equals 2? And if you're kind of indifferent between all the possible functions, the training data doesn't actually force you to pick one, or it doesn't favor one over the other. So this is a sense in which there's no free lunch, right? Unless you decide a priori that you believe certain structures are more likely than others. And we'll get to that. How do we know that we should expect some things to be more likely, right? If you don't have any prior inductive bias. So if you're Bayesian, your inductive bias is just your prior. But frequentist methods also have inductive biases. So this is important. So should we guess the identity? Well, why not? I don't know. Here's a function I cooked up that happens to also fit the training data, but predicts a very different f of 0. Why not use f2? Why not predict that the function is actually f2? And classically, you say something about kind of simplicity. What is simplicity? Well, in classical statistics, it's kind of the size of the hypothesis class. And size is a very generic term I'm using. Maybe some formal term you'll use. It would be, well, for finite sense, maybe it's just a cardinality, but maybe you want something like VC dimension, Some notion of model size or capacity, right? So here is a small class, right? F1 is simple because it belongs to the class of linear functions. This is a small class. You don't overfit, surely, if you fit to H1. Okay, but here's a class that's equally small, but contains F2 instead, right? I just hard-coded F2 into the class, right? It's like linear functions plus F2. Or you can think of it as you like hard code the x cube and x. Yeah, you hard code like the leading coefficients. So why not pick H2? And what's remarkable is that there's a symmetry, right? Because if the function really is F1, then H1 is a great class and H2 is a terrible class. But if the function really were F2, then H2 does really well and H1 doesn't. So if you just use classical statistical learning theory type bounds, you get identical generalization bounds. These classes have equal capacity. So they're like equally good as far as the classical theory is able to tell you. There's something remarkable that maybe is obvious, but I think people forget. That statistical theory doesn't tell you which of these to prefer. So why do we prefer F1 H1? So one proposal is that, okay, we actually do have an inductive bias. This inductive bias comes from all your past experience. It might even come from evolution. You've evolved to have certain inductive biases. The problem with that argument is that your past experience or your evolution, these are also learning algorithms. So you're basically meta learning at a higher level what your inductive bias should be. And that's the exact same form of problem. Like formally, you could imagine like now you're learning a meta function instead of integers to integers, it's integers to functions from integers to integers. And you run the exact same no-free-lunch issue. There are equally many kind of meta functions that are compatible with all the functions you've seen so far. So it's often said that if you're in kind of a realistic setting, right, then of course learning works and generalization works. You can just use an inductive bias tuned to that setting. But that's still kind of cheating. Like, how did you know you're in that setting? How did you decide which inductive bias to use? So like now you kind of raise the problem up a level to the meta learning. And you know, in the history of statistics, we've kind of this kind of hasn't mattered so much because we haven't really tried to build AGIs, you know, historically. So it's okay that the human beings have great intuitions, and we just need the theory to tell us how to like test our hypotheses. But the theory didn't need to tell us where those hypotheses from, because human beings come up with them. Now, okay. So yeah, but now we actually want to understand each other. We want a self-contained theory of intelligence. The AGI needs to fully generally, you know, it can't be too bound to our inductive bias. It needs to like fully generally be able to kind of come up with whatever structure or patterns it needs autonomously. And we'd like to understand these AGIs as well. So a fully self-contained theory of learning needs to address no-free-lunch somehow. Yeah, we have this theorem. So actually, we can visualize the no-free-lunch situation too, right? Like we could pick this giant hypothesis class H0, but the theory says if you pick the giant hypothesis class H0, you won't underfit. You can like fit any training data you like. So your training loss will be good, but then your generalization gap is terrible, right? Or you pick a small class like H1 or H2. The problem is if you pick a small class, the classical theorems tell you that the generalization gap is good. You know, there's a difference between test and training loss. That difference is good, but it doesn't say anything how good your training loss is, right? So if you pick H1, but your true function is H2 is F2 or vice versa, it doesn't work. So visually, what no-free-lunch says is that you'd like to pick a small class, but you'd like that small class to also be close to your true function. And the no-free-lunch is that this is not possible, right? You can't pick a small object, a small circle, and still contain all the possible points. And that's the issue. And by the way, soft preferences don't overcome this. I've kind of simplified by just choosing hard hypothesis classes, but you run no free lunch is very general. It's not just the worst case result, it's an average case result. It could cover soft preferences, it covers literally any algorithm you could use. So fundamentally, you can prove one or the other, but you can't prove both for the same method unless you make assumptions about your domain. But then the question is, how do you learn which assumptions to make? Okay, so here's a better proposal. Well, or at least partway there. It seems F1 is just easier to think of, right? You could imagine living in a world where F2 is the truth, but if F2 were the truth, you kind of it's hard to think of a realistic method that would guess F2, right? Like we only figured out F2 by seeing the data first, like hard coding F2 into it. So so F1 is like more guessable, and the classical like combinatorial view does not really distinguish between F1 and F2 because they're both just functions. But from the point of view of say Kolmogorov complexity and computability, it's clear that F1 is simpler. That doesn't quite solve it. It's like simpler relative to like what Turing machine. This is actually really important. But in some sense, this gets to a new idea by the philosopher Gerard Schertz, who, well, he recently wrote a book called Hume's Problem Solved. Hume is known for the famous problem of induction, the hundreds of years old philosophical problem about exactly this, how you justify inductive reasoning. And he basically says that you can't solve it in general over like the class of all possible inductive methods you mathematically could use. But if you think about which methods are accessible to you, and your meta induction works by just selecting among the smaller class of accessible methods, then this setting is exactly what machine learning experts have called prediction with expert advice. And this setting is solvable. The combinatorics do work out. And one way to see this is that if you have a sequence of like say n bits, there's 2 to the n possible like sequences you could imagine fitting to, and you'll just never have enough information to distinguish between 2 to the n possibilities. But in the expert setting, there might just be like 10 possible candidate sequences, and you can kind of just by process of elimination, there are algorithms that ensure that you do at least as well as the best of those 10 experts. So Schertz is a philosopher. He does actually seem aware of Kolmogorov complexity, which is cool. But I think we can make his ideas more precise by really taking logarithmic information very, very seriously and take computation more seriously. So an algorithm's code is itself data. And we should really take this as a first class intuition going in, right? When we're optimizing over possible algorithms, like we're actually, what is the best prediction algorithm? Well, if an algorithm just hard codes the test set would kind of be the best possible thing. Like it would just predict really well. Or even a finite, if it's infinite, just imagine like some finite portion of everything, you'll predict really well for a long time. So, but you're not allowed to do this. It's cheating, right? You can't, you don't want to counterfactually imagine the best out of all possible pieces of code, because then you could just hard code data. Code is data. So really what you want, like you can't magically materialize code. And that's, so it's actually a bit of a contradiction in asking what's the best learning algorithm. Because if you're an AI inside a computer trying to like predict what's the best prediction you can do, if you live in a deterministic universe, like you're bound to run your own code. Like there is no choice, right? There's no free will in that sense, right? But but you can imagine like what's the best intelligence that would evolve? What can you like? If you imagine evolution as like sampling random algorithms in a computable world, what's the best you could do? Or more formally, one way I like to think about it is let's counterfactually optimize over code, but only like a small amount. but the small amount of new code is able to use the computers and data that are in the world around us. So you're allowed to use complex algorithms, but only if you could generate it from what's around you plus a small c. So you're only optimizing over like, say, programs of length up to like 1,000 bytes, whatever, just make up some number. But then this program is like connected to the internet. So you could download open source repository, they could read books, you could download data sets. So, and our goal is to just perform as well as any algorithm that is accessible in such a way. And the reason is that we can't, there's no plausible way we could have done better. And we might wish we used the ideal UTM that like actually hard codes the test set, but we don't have that UTM, right? I promise there's more math in the paper, but so, you know, this is the diagonalization argument. We can't actually be universal over all computable methods while still being finite time computable. So this is where you kind of take the limit of like a computation that runs to infinite time and you end up with Solomonoff induction. But it's Solomonoff induction relative to what I'm calling an information vantage point. So the idea is there's like some, like the UTM is kind of given to you. You actually have a choice. You know, if you're given 3 UTMs, then, I mean, you to make this really precise, you have to imagine that you're like, just to get rid of our fuzzy human intuition, just imagine that you're like inside a dash terminal or something, figuring out the optimal thing to do. Then that interface determines what your UTM is, right? Like maybe you have 3 computers, but you're accessing those 3 computers through your like interface, right? So that interface determines your like base UTM, which like, you know, can like, you know, can use that interface to access whether, but there's like, yeah, so there's, so you essentially you can combine all the computers and data that you have into one base UTM, and you're kind of stuck in that frame. So I found that it's expedient, it's useful to formalize this as a UTM that's relativized to an oracle Q. So you can imagine U is like your Unix shell, that's your UTM, but then Q is like, formally Q is just an extra tape on your that your UTM has access to. But intuitively, you should think of Q as containing all of the data on the internet. You know, if there's like other UTMs you have access to, maybe you access them through like interpreters that you understand. Again, you could imagine just getting rid of Q and hard coding it inside you, but it just turns out that this is helpful because then we can all agree on what base UTM, like a shelling point where you all know. Like we all have different, right? Like I have different knowledge than you do. I can only be optimal using the knowledge I have, right? If I don't have the knowledge you have, I can't hope to predict. And then you can kind of interpret the optimality results that are usually proven throughout Solomonoff induction in a nicer way. So in a way that makes sense on finite data. So it's crucial. I don't view Solomonoff induction as something that's asymptotically optimal as you extend the sequence to infinite length. Instead, these constants can be bounded. You just choose your UTM in such a way that the specific theorem in the paper has like a, like the constants depend only on you, but you fix U once and for all. And what you get is a result like this, where your regret of your Solomonoff induction against some other computable method is bounded by how much mutual information there is between the this other program and your like sequence X. So this just means this predictor, and this is a sequence, like a finite sequence. And this is like not the usual algorithmic mutual combination. It's actually defined as just you know, in terms of like the KM complexity. I think it's too important how it's defined, because you can just view it as intuitively representing how much information P kind of hard codes about X. And it's relativized to Q. So that means the non-efficient this rival predictor has about the data that isn't already captured by the vantage point Q. So in some sense, like your regret is now bounded by a finite amount. That finite amount could be large, but only in the case where you have this. So you only have high regret against an algorithm that that kind of in some sense has a lot of knowledge about the data set built in, which you don't have. So therefore, like you shouldn't feel bad about losing to this algorithm. Like there's no way you could have reached that level from setting. And that's the key thing. Like programs are data, they are information, and information cannot be algorithmically generated, right? There's no meta algorithm you could have used to invent a smarter P, right? Like you usually imagine, hey, we're like really smart, we can come up with better machine learning algorithms. There's just no algorithmic way to generate your learning algorithm could cause this initial information to become higher than what you started with. And since we've relativized to what you started with, actually, it's like almost zero. Yeah.
Does this kind of just become vague? Like if I think of like I have some prior, right? So like posterior mass because of that prior over something. Roughly the complexity is like the volume of the inverse volume of the posterior mass. Like, is this kind of just the same?
The difference is we're really like we're narrowed down what the base prior is. So
The prior is just like
yeah. Well, this is the prior that kind of tries to maximize the amount of mass everywhere. Tries to, but the accessibility is a constraint. So you might wish that you put a lot of mass in hypothesis 5078 because that's actually the best one. But if you didn't have a pointer to number 5078, you can't do that. But the information vantage point is important because, for example, if you are familiar with the script of Hamlet, then you can actually predict. We see the beginning of Hamlet, and you're like, oh yeah, I know this, right?
I guess what I'm asking is like from a pedagogical point of view, it'd be interesting to like show us how like exactly how this would what Bayes would do.
To what Bayes would do. I mean, Solomonoff induction can always be very naturally interpreted as a Bayesian. I mean, like actually in the setting, any predictor can be viewed as Bayesian with different priors, right? I mean, in this setting that we're considering, I mean, you could generalize, but in the main setting we're considering, really, the game is like we see it's one at a time. We predict you predict a number from 0 to 1, which interprets probability, and your reward is like the scoring is that you get log of that. But if you're predicting a number between 0 and 1 at every point in time, that algorithm can always be interpreted as a Bayesian algorithm because you just reinterpret those numbers as conditional probability to the next bit given.
But more specifically, the Bayesian algorithm is the competitive prediction algorithm we want. So this is like it's literally exponential ways. So it's true.
In this setting, there's no such thing as a non-Bayesian algorithm.
Oh, okay, that's right. But given your set of predictors that you want to beat, then the correct algorithms have bounded log loss against those predictors. The Bayesian algorithm is that off of this space. So this really is a justification of Bayes.
I don't think it followed.
So you're trying to beat all the predictors you have access to in terms of log loss, to a constant. The algorithm that does that is Bayesian. That's like one justification for Bayesian updating space, competitive prediction of the log loss.
I mean, I feel it's more like a justification of a specific prior, since the other algorithms are also Bayesian.
Yes. So your paper is justifying the universal distribution. This particular prior over programs that comes from accessibility. But which is like the novel contribution, but it's Bayesian because it's lots of those.
I mean, also it can be viewed as like it literally is a mixture of like all the accessible things, like the universal Solomonoff mixture, so it's more explicitly Bayesian sense, I guess. Maybe I didn't fully get it.
Yeah, that's right, but that's because you ought to.
Yeah. Maybe this is something I didn't get. We can talk. But I mean, so is the conclusion slide. The point really is that I don't think like algorithmic efficient theory gives a nice answer to meta no free lunch, as long as it's slowly framing. And as far as I know, no other approach does this. So we have a whole appendix in the paper that talks about kind of classical theorems and statistical learning theory. None of them really tell you anything about which inductive bias to use. It just says you pick a small class, of which small class, right? Like in that figure I had drawn. So this is so you kind of uniquely need computability theory to make sense of inductive biases and generalization. Generalization is like the biggest problem we'd like to understand in learning theory. So in other words, everyone should be using algorithm information theory. If there's an alternative view, I'd like to hear it, but it seems that's really the case. And I also want people to stop saying that Solomonoff induction is only good in the limit of infinite data. It is infinite time. I concede that, but it's not infinite. You don't need infinite data. Once you have the vantage point thought out, it's actually optimal up to like pretty small clusters. Yeah, that's.
Could you also say something about because I actually think the most frequent justification is the Occam's razor, right? So you also say something about that?
Indirectly, I suppose, because I just view it as less optimized. Let's just see how like what an optimal learner looks like, and it's Solomonoff, and there's some sense in which we understand Solomonoff is preferring short programs. But it's not like I start with Occam's razor. It's sort of like, yeah, it's something that emerges out, and yeah, and it's a more careful version of Occam's razor because it basically says that I should use kind of small C programs, but this small C program is allowed to use all of my knowledge and data already. Like, I don't know, I think we're a bit sloppy sometimes, so it's good to like make theorems and like precisely what it is we're saying and use that as the intuition box.
Yeah, I mean, I just think it's important to point this out because I think generally people sort of in this symposium want to somewhat justify machine learning methods through Occam's razor, and then just treat that as sort of the end of the story, right? Like, okay, now Occam's razor is justified by AIT.
Yeah.
But I think we actually need to be more careful about this.
Yeah.
Where actually is the justification of Occam's razor?
I should also add that in some sense, I mean, this is a criticism against Occam's razor that a lot of people throw out, which is that like basically any prior can be interpreted as Occam's razor. If you're not, you can always, and especially on finite data, because on finite data, even the Como graph complexity tune out really like. So like literally choose any prior you want and interpret log one over that probability as being code length, and then literally any prior is Occam's razor. And statistical learning theory presents various kind of notions of simplicity and complexity of classes. These can also be interpreted as Occam's razor. So like there's a lot of versions of Occam's razor out there, but you gotta commit to a specific prior, and then you run into no free lunch. It's like, okay, how do you choose like which prior, which coding system to use? And the answer is the one you have access to, or one that's universal over everything you have access to.
Yeah, that's something maybe I still don't completely get. I mean, you're still fixing one universal reference computer, right? And this is, there are many of them that can be also arbitrarily different from each other, and still the universal. So there's still some kind of arbitrariness in fixing that.
Well, you don't have access to every possible universal machine. So what's your concern? Is it that you have like 5 different computers in mind and you don't know which one to set as your reference? Because you definitely don't have access to all of them. Right? You have your brain, you have your laptop, but you don't have all the Turing machines. Like physically, you just don't have them.
Yeah, okay, that is true. Okay, if we talk about physically access to, then then we have to somehow figure out how these machines that we have access to solve the key.
It's a bit tricky to operationalize. Again, if you imagine yourself as being made of digital code inside a computer, I think it's easier to make this precise. But because we're like squishy things, it's a bit harder. But still, I think the argument's similar. And in some sense, like you can just use Q to encode all the different like programming languages. You just write code for their interpreters. And so I like to just think of you as like just pick any shelling point, like any one language that we all know, and like let Q be kind of the personalized part that are different between us. I think this is a convenient way to conceptualize this that works. I think there's a few different like equivalent ways. Like maybe there's like 3 different shelling points used, but it won't matter which one you choose because the other 2 will be encoded inside Q. And so you can switch between those at very minimal cost.
Yes, yeah, okay, I agree.
Yeah,
and in the total abstract, it doesn't really work. But if you get, if you consider somehow realistic setting, it seems like
Yeah, and
But then aren't we just back to like our naive notion of complexity from a statistical lens would be like, okay, my prior somehow tells me what I expect to see. This kind of encodes a notion of complexity, but then it's arbitrary, it's just relative to my curve. So then people will go from that and they'll learn about overall complexity and they're like, oh my gosh, there's this objective notion. Then you see there's these large constants for finite strings, and also it's relative to your UTM. And it goes back to being subjective. But then now you've taken it back to some sense another prior. So I'm confused,
it's, I guess we're kind of agreeing that it is sort of subjective because Q is like part of your reference point. Like if Q is finite, you can always hard code Q into your Turing machine. But again, I prefer to just fix U so that it's just easier to do theory with a fixed U. But different agents should be using different reference points. Yeah. So the reference point is subjective.
But is it fair to say that as Q gets bigger, as you sort of accumulate more prior knowledge, you in some sense get less subjective?
No, that's not true. So first of all, getting more knowledge doesn't even improve your situation unless that knowledge is actually good. Like imagine the library of Babel. The library of Babel has all the books that are possible to write. And it is also completely useless. There is a short program that prints the whole library of Babel. So you're necessarily picking an inductive bias you're not picking it. Q is your surroundings.
Yes, sorry, I don't know.
Yes.
Just read your conclusions.
Yeah. Oh, did I not say anything? Oh, yeah. So, so of course it's idealized, and point is we should, we don't actually Solomonoff induction, but there's a lot of new work, time bounded, whatever, complexity, mutual measure researches more. There's new work that says neural networks. The success of neural networks took the whole community by surprise. We still don't really have a good theory for why they work, but statistical learning theory just doesn't even tell you what the inductive bias should be, right? It's just okay, it has this inductive bias, but why is this good? So, but there's an emerging line of research that says, okay, maybe these neural networks, because they kind of look like general circuits, and then you add recurrence, you add memory, and you get something like a UTM. So maybe what's happening is that modern machine learning methods are moving closer in the direction of universal computation, and that's why they work. If you were in the field 10 years ago, the whole world was hey, this is so unscientific. Why is ImageNet being won by this unscientific method called deep learning? That was the move, right? It's very unprincipled. So yeah, but if you knew about Solomonoff induction, maybe you'd be less surprised in retrospect.
The